Hello. So, my dear friends and dear students, welcome to the class. Dear students, today we will discuss a new topic from quantum mechanics that is called particle in a box. So, directly I am writing here that particle in a box. Clear? So we'll discuss the problem on particle in a box. Clear? Now whenever the particle in a box problem is given or the system is given, always remember the potential will be given. Clear? So let us define the potential as, that Vx, this Vx is equal to, it can be defined as 0, and when the limit of x is x 0 less than x less than a, it means the width of the potential is a. Clear? And that is equal to infinity otherwise. Clear? So if I draw the potential, it will be just like this. That means the width of the potential is a. So if I say this position is 0 and this is suppose a, so this width is a, and it is given that when x less than x is between 0 and a, that means the potential is equal to 0 here, and otherwise it is infinity. It means outside the boundary in this region the potential is infinity, is this region the potential is infinity, as well as on the boundary the potential is infinity, on the wall that is potential is infinity. Clear? So this is our potential. So 1D potential, this is 1D potential. Now what will be the solution of this potential if I solve it using Schrodinger equation or any other methods? Then I will get the energy eigenvalue as well as the different wave function. Clear? So the energy eigenvalue I can directly write here, that the energy eigenvalue will be, it will be, E suffix n is equal to n square pi square a square upon 2 m a square, where this a square is a Planck's constant, a square is equal to h upon 2 pi. Clear? And this m is the mass of the particle and this a is the width of the potential. Always try to remember that this is just not like that, this is a square. So try to remember it is, this a means width square. Sometime when the potential width is suppose 2a, from minus a to plus a, then which will be twice a, then it will be twice a whole square. Clear? And the wave function will be your psi nx for nth state, that is equal to one normalization constant that will come is equal to under root 2 upon a, 2 upon width. Clear? And sine n pi x upon a, sine n pi x upon a. So this is the wave function. Always remember this is width, Clear? Now, so this is a 1D case. So whenever we discuss the degeneracy or what type of degeneracy in case of particle in a box, then we have to discuss about the 2D case or the 3D case. Clear? So now let us take a 2D potential. Where we can very easily discuss all those things. So by knowing this all values, we can construct the 2D box, or just I am writing that 2D box. That means particle in 2D box. So the potential will be given like this, that V, two variables will be there. Vx and y I am taking, and that is equal to your this 0 when 0 less than x less than a, and your 0 less than y less than a. Clear? So, and that is equal to infinity otherwise. I am writing otherwise. Clear? So that means in 2D case, that means in a plane, if I draw the potential, so it will be just like this, that if I draw the potential, it will be like this. Suppose width along x-axis and width along y-axis, here it is given a. So this is suppose y-axis and this is suppose x-axis. If the width is a, that means 2D potential, 2D, so it will be in x-axis 0 to a, 0 to a, and in y-axis also this is a. From this to this distance is a, or from this to this distance is a. Clear? Or you can write down the coordinate. This will be 0, 0, and this will be a0. Clear? This will be 0, a, and this will be a. So this is the 2D potential, where the potential V is equal to 0, 0 inside this box, and V outside this, all in this case, in this case, in this case, and on the boundary. In all other cases the potential will be infinity except this inside region. Here it will be 0. Clear? Now then what will be the solution? Energy eigenvalue. So one can find out the energy eigenvalue like this. Energy eigenvalue will be your that En, I am writing En x n suffix x and n suffix y, because here I am taking 2D case. So here I am taking 2D case. So to distinguish the energy eigenvalue in x-axis and y-axis, here I am writing nx and ny. It means that this will be, energy will be En suffix x plus En suffix y. Clear? Now what is the value of En suffix s? Instead of n, here I am writing nx, and instead of n, here I am writing ny. Okay, so don't get any confusion. Nx will be, for this is the width is a, so it will be the nx square pi square a square square upon 2m. What is the width along x-axis? This is a square, plus, and that along y-axis this will be ny square pi square a square upon 2m. What is the width along y-axis? That is also a, so it is a square. Clear? Or further I can solve it. That is equal to, see, this pi square a square by 2m a square is a constant, so I can take that pi square a square upon 2m a square is a constant. I am taking it as a common, so n x square plus n y square. Clear? Or further I can write here that nx square and ny square, I can write it is an n square pi square a square upon 2m a square, where this n square is equal to, I can write an x square plus n suffix y square. So this is an important relation. This is an important relation. So one has to find out to calculate the degeneracy of different energy levels. So I hope this relation is very, very important and you got the idea. Now we'll move to how we can calculate the degeneracy as well as different energy level and the wave function of different energy level. So let us see. So to find out the degeneracy or different energy eigenvalues of different level, so here our nth state energy eigenvalue is this, where n square, I got that nx square plus ny square, and this nx and n value, nx and ny value will start from 1 2 3 dot 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 and so on. Clear? Now what will be the value of the ground state energy level? So for that I have to put the different values of nx and ny. So let us take that nx and ny equal to 1 1 1. That 1 1 combination will give you the ns square value equal to 2. So the energy eigenvalue corresponding to this combination, this will be E11, 2 pi square a cut square upon divided by 2 ma square. Clear? Now for the combination 1 2 and 2 1, so n square value will come out as 5. So for these two combination, that E12 and E21, this will be 5 multiplied by this factor and 5 multiplied by this factor. Now you see that this factor and this factor, these are all constant, but between these two energy eigenvalue, so here I am getting the lowest energy, so this will term as a ground state. GS means ground state energy eigenvalue, and whether this is fast or not, for that I have to take another combination. So let us take that 2 2 combination. I will get n square value here 8. Now see, in between that n square, when I get 2 2 combination, the energy eigenvalue E22 equal to this. Now in between this terms are constant. So only the difference I am getting that n square value. Here I am getting 5, here I am getting 8. Clear? Now 5 and 8, 5 is lower, but this 5 is greater than the ground state energy eigen value. So this is that is why I can term this is as a first excited state energy eigen value. Now please remember that while finding the different energy eigenvalue, remember that ground state is the lowest possible energy eigenvalue. First excited state is just greater than the ground state, and second excited state just greater than the first excited state, and third excited state just greater than the second excited state, and so on. So this is the first excited, and for second excited state let us take another combination here, that 3 1 and 1 3 combination. Here I will get n square value will come out as 10, and so the E13 and E31 combination, the value will be energy value will be this, but in between these two, 8 is lower than 10, but this 8 is greater than the first excited state, that means this 5, because these all terms are same constant value. So that is why this is termed as a second excited state energy, and this will be your third excited state energy. So for confirming whether it is third excited state energy or not, so I can take the 2 3 combination, next possible combination 2 3 and 3 2 and 2 3 combination. So here I will get 13 pi square a square upon 2 ma square. So this value is lower than this value, and but this value is higher than the second excited state, so that is why it is third excited state, and so on. And for finding the fourth excited state, you just take any next combination and see whether this combination is greater than the later combination, or lower than the later combination. In this way one can find out the different energy level. Now while finding the degeneracy of the different energy level, so I have to find out, I want to write out the wave function of different energy level. So for the nth state, I can write down the wave function psi nx ny will be a function of x and y. Since wave function is multiplicative, so psi nx will be a function of x, psi ny will be a function of y. But since the width is a, so it will be a normalization constant under root 2 upon a psi nx pi x upon a, and for psi ny, so under root 2 upon a sine ny pi y upon width is a. So if I further calculate it, it will be under root 2 upon a, under root 2 upon a, it will be 2 upon a sine n pi x upon a and sine n pi y upon a. That means, so this is our the wave function for an nth state. Now what will be the wave function for the ground state? For ground state, I took that nx and ny values are 1 1. So nx and 1y value, that is why I will put here that psi 1 1 xy is a variable, so 2 upon a nx I have to put here 1, nx y I have to put here 1. So this is your the wave function. So corresponding to this energy ground state, I am taking only, I am getting only one wave function. So one can say that the degeneracy for this first excited state will be 1. Clear? Ground state, degeneracy for the ground state will be 1. So the degeneracy for ground state I am getting, that is equal to 1. Now what will be the degeneracy for first excited state? So the first excited combination 1 2 and 2 1 combination. So the 1 2 combination, here I have written here the nth wave function, nth state wave function. 1 2 combination I will get 2 upon a n a, that means nx I have to put here 1 and ny I have to put here 2. That is why sine n pi x upon a sine 2 pi upon y upon a. Clear? And for 2 1 combination, that means nx equal to 2 and ny equal to 1. So this will be 2 upon a, so 2 pi x upon a and sine 2 pi x upon a and sine pi y upon a. Now corresponding to this level, the energy eigenvalues was this amount, the energy eigenvalue, but this two energy eigenvalues are same, but this two wave function corresponding to this energy eigenvalue are different. How? See, although for these two wave functions the normalization constant are same, but here I am getting sine pi x upon a, here I am getting sine 2 pi x upon a, here I am getting sine 2 pi y upon a, here only I am getting sine pi y upon a. So for this nx and ny, different values of nx and ny, I can say that these two wave functions are different. That is why that different two wave functions I am getting corresponding to this first excited state. So the degeneracy here I can write 2. But what type of degeneracy is? See that nx and ny value are exchanging between these two wave function. Nx here it is coefficient is nx is 1, here it is 2, here it is ny is 2, here it is 1. So the 2 1 value, 2 and 1 number are exchanging between the nx and ny, I mean between the two wave functions. So that is why this type of degeneracy is called exchange degeneracy. Now what will be the this is the degeneracy for first excited state. What will be the degeneracy for second excited state? Second excited state, we got the combination 2 1 or 2 2 combinations. The wave energy eigenvalue is this. So the wave function will be psi 2 to xy, this 2 upon a psi 2 pi x upon a psi 2 pi y upon a. So therefore only one wave function we are getting corresponding to this level. So degeneracy is 1. Now what about the third excited state? We got the third excited energy eigenvalue 1 3 and 3 1, that is 10 pi square a square upon 2 m square. But for 1 3 combination the wave function is this, and because nx equal to 1 here and ny equal to 3 here. For 3 1 nx equal to 3 here and ny equal to 1 here. But here I'm getting these two wave functions are different, because you see sine pi x upon a and sine 3 pi x upon a. Here sine 3 pi y upon a, but sine pi y upon a. So 1 and 3 because in here are different in these two wave functions. Here 3 not present, here 3 present, here 3 present, here 3 not present. So these two wave functions are different, but their energy eigenvalues are same. So it is a degenerate case for this third excited state, and the degeneracy is 2. I am getting 2 wave function. And what type of degeneracy? You see 1 and 3 are here exchanging, so this is called exchanged degeneracy. Clear? So I hope you got the idea how to find out the degeneracy. Similarly, we can find out the degeneracy for other level also. For suppose fourth excited state, fifth excited state, you can find out the degeneracy. But dear student, I want to mention here that so for finding the degeneracy and what type of degeneracy will be, so no need to write down the wave function. For competitive examination, one can find out from the earlier expression. I will show here. Here I have moved to the previous pages that when you got the nx square equal to n square equal to nx square and ny square, here from here also you can find out this calculation. I have done it elaborately because of your understanding. Once you are expert, you can easily find out directly the degeneracy. Now see 1 combination, here I will get only one wave function. Clear? Just we have to recognize the different energy levels. So this will be your ground state, this we got the first excited state, this we got the second excited state, this we got the third excited state, this we got the fourth excited state. Clear? So and so on. Now corresponding to this combination we will get one wave function. Corresponding to this combination, the number of combination will give you the number of wave functions. The different wave functions will be anytime different because these coefficients will be different. So here the degeneracy will be 1, I can say. For first excited state degeneracy, different combination, so the degeneracy is 2. Here for second excited degeneracy you will get 1. For third excited state degeneracy you will get 2 because 2 different combination. For fourth excited state you will get degeneracy 2 because for different 2 combination. Similarly, the rest also one can find out. Now we will move to the 3D case. So how can we find out the degeneracy and energy level? So in 3D case, I will say that 3D box, particularly in a box in 3D case. So that the potential will be given as Vxyz will be 0 when x limit is 0 to a, and y limit is 0 to a, and z limit is 0 to a, and it will be infinity otherwise. That means if I draw the potential in 3D case, it will be a just cubical box. In x-axis, y-axis, z-axis, and the width along x-axis is a, width along y-axis is a, and width along z-axis is a. That means the potential inside this box, the potential will be 0, and the outside the box and as well as on the boundary of the box, that on the walls of the box, that the potential will be infinity. That is the meaning otherwise. Clear? Now what will be the energy eigenvalue? Instantly I can write that Enx and y and z will be Enx plus Eny Enz. So for Nx I can write Nx square pi square a square upon 2m. What is the width here along x-axis? The a. So width square. Similarly for this, Nz square pi square, width along z-axis is a. Clear? Now since pi square a square upon 2m square constant, so common, I can take it as a common nx. So here I will get nx square plus ny square plus nz square. Now further simplification, I have written nx square pi square a square upon 2 ma square, where I got that nx is square equal to n is square equal to nx square plus ny square plus nz square, and all these nx, ny and nz value will start from 1 2 3 4 dot 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 so on. Clear? Now what will be the this is your energy eigenvalue for nth state. What will be the energy eigenvalue for ground state? For that, the minimum possible combination, minimum values we have to take. So nx, if I take nx equal to 1 and y equal to 1 and z equal to 1, then 1 square I will get n square value equal to 3 here. So corresponding to this combination, the energy eigenvalue, the energy eigenvalue will be your E111, that will be 3 pi square a square upon 2 ma square, and for the next possible combination I can take that 2 1 1 combination, then 2 square 1 square and 1 square, nx equal to 2 and y equal to 1 and z equal to 2. In this case we will get 3 possible values combination, and in all these 3 possible combination I will get n square value will that is equal to 6. So the energy eigenvalue corresponding to this combination is E211, E121 and E112, that will come out 6 pi square a square upon 2 ma square. Now in between these two, which one is the lowest? So this one, see this factor and this factor, this is a constant, this is a constant, here 3 and here I am getting 6, so 6 is lower, so this is the minimum value. So I can say this is GS, means ground state energy level. Clear? Now for first excited state, so I can take the another possible combination, that 2 2 1 combination. So nx and ny value suppose 2 2 and nz value is 1, so 2 square plus 1 square, so that will come out n square value is equal to 9. So that energy eigenvalue for that 2 2 1 2 2 1 2 1 2 1 2 2, that will 9 pi square a square upon 2 m square. But in between these two, this 6 is lower than 9, but this energy eigenvalue is greater than the ground state, so I can term it as a first excited state energy eigenvalue. For second excited state, let us take another combination, that suppose let us take another combination. Suppose here I can take 2 2 2 combination. Clear? That 2 2 2 combination, and also I can take that 3 1 1 combination, another combination 3 1 1 combination, the nx equal to 3 and y equal to 1 and z equal to 1. In this combination 3 1 1, so here I will get three possible combinations here, three possible combinations. Here I will show you this. So 3 1 1 and 1 3 1 and 1 1 3, but corresponding this all combinations I will get n square value equal to 11, but here I am getting that n square value equal to 12, but 11 is lower than 12, but our comparison is whether this is second excited state or not. So but this 9 is lower than 11, but this 9 is this energy eigenvalue is greater than this first excited state, so I will term as a second excited state. Now this will be in between this 11 and 12. So I will get the energy eigenvalue here lower than this, but this energy eigenvalue is greater than the second excited state, so I will term this as a third excited state, and this will as a fourth excited state, and so on. One can easily find out. Clear? Now what will be the degeneracy for this energy level? See, for ground state, for this ground state, that how many combinations we have got? Only one combination, so the degeneracy here it will be 1. For this first excited state we have got 3 combinations, clear? So the degeneracy, because in 3 combinations we will get 3 different wave functions, clear? You will get 3 different wave functions, but the energy eigenvalues are same, so the degeneracy for first excited state is 3. Similarly for second excited state I am getting 3 combinations, so but for each combination the wave function will be different, so the but their energy eigenvalues for each combination will be same, so the degeneracy for this level is 3. And for third excited state here I am getting the degeneracy is again 3, and for fourth excited state the degeneracy is 1. In this way, this is the simplest form to find out the degeneracy of different energy level. No need to find out the wave function. Wave function for any competitive examination, just you have to you are asked to that find out the degeneracy of the fifth excited state or fourth excited state. Just you proceed in this way and find out the different combination, number of different combination for that certain energy level, because for each combination the wave function will be different. Let me check one first for first excited state, so this whether the wave functions will be different or not. So let me check. For first combination, first excited state E211, E121 and E112, we got the energy eigenvalue. In all energy eigenvalues are same, 6 pi square a square upon 2 m square. But for any excited state, the wave function will be psi nx, ny, nz will be a function of x, y, z. So I can split in this way. Psi nx will be a function of x, psi ny will be a function of y, psi nz will be a function of z. Now what is psi nx? With is a, since in all cases, so under root 2 upon a sin n pi x upon a, under root 2 upon a normalization constant sin n y pi y upon a, and under root 2 upon a sin n z pi z upon a. So this is our cases, this is our wave function for nth state. For this is our further simplified form. Now for first excited state, the combinations are, since 2 1 1 1 1 is the combination, so x y z will be a variable, so 2 upon a 3 upon whole to the power 3 upon 2, that means 2 1 1 means nx value will be 2 and y value will be 1 and nz value will be 1. So nx 2 n pi x here, ny 1 here, the pi y by a, and here nz was there, so putting nz equal to 1, pi z upon a. But for 1 to 1 I have to put here nx equal to 1 and y equal to 2 and z equal to 1. So putting this all values I will get this combination. You just put nx and ny and z value here. So here psi 112 is means nx equal to nx equal to 1 and y equal to 1 and z equal to 2. So I'll get here sin pi x by a, sin pi y by a, sin 2 pi z by a. These all wave functions are different. How? You see, you just although the normalization constant are same, but here you see sin 2 pi x upon a and sin pi x upon a, sin pi x upon a. Here sin pi y upon a, sin pi 2 pi y upon a, sin pi y upon a. See, so this wave function, this wave function, these wave functions are all three are, you just compare, you just look at the wave function carefully, you will get that these all are different. So but their energy eigenvalues we got that all three combination energy eigenvalue we got equal. So equal energy eigenvalue but different wave function you are getting, so the degeneracy here it is 3. Clear? So we have verified that the degeneracy for first excited state we got 3. Similarly for second excited state, third excited state, fourth excited state, one can easily find out. Clear? Here I am just I have checked whether the wave functions are different or not. Wave functions will be always different for different combination. Please remember, and no need to write down this for in your competitive examination. Otherwise for your semester examination one can write down. But if for better understanding, so just I have written here. So hope in this way, so we have got the idea how to find out the degeneracy energy level of a particle in a box in 1D, 2D and 3D case, and how to find out the degeneracy of a certain energy level and what type of degeneracy, whether it is exchange. Exchange means when the nx, ny, nz value are just exchanging between the wave function, then we will say exchange. And when it is not exchanging, then we will say accidental degeneracy. Clear? So this is a simplest form I have discussed here. If you think that this is a very helpful, so please do share my YouTube channel and like it, subscribe it and share with your friends. So thanks to all of you.